here from Karl Schwede, University of Utah, about perfectoid spaces and multiplier /test ideals. And if you're like me and you know close to nothing about perfectoid spaces, well, you know, that's our chance to learn, right? That's what time is about. Hearing about new flavors of algebraic geometry, you never know what they're going to study next.
So I have to say, if you were hoping that I would teach you all about perfectoid spaces, you're going to be sorely disappointed. I mean, I know some theorems about them, and I know a couple places to use them, but you know, my co-author Linquan Ma understands the nitty-gritty of perfectoid spaces much better than I do. But what I'm really talking about today is a mixed characteristic singularity theory in sort of algebraic geometry, commutative algebra. And so what we're going to do is, I assume most people have at least heard of multiplier ideals before. And there's a characteristic P analog called test ideals, which are defined somewhat differently. And what we're going to be doing is talking about some analog and mixed characteristics, so like over ZP, the p-adics, which have a lot of the same properties, or at least we're starting to show they have a lot of the same properties. And like I should say, this is all joint work with Linquan Ma. Okay, so I'm going to start here. So let me just remind you about multiplier ideals. And let me remind you of some different ways to think about them, which will help motivate our eventual mixed characteristic definition. So let's say X equals spec R. I don't know if you want R, it could just be a polynomial ring. Say, let's say I have some kind of ideal A inside R, right? If you'd like to think geometrically, Z will be the vanishing locus of A. And I'm going to fix some real or rational number bigger than or equal to 0. Okay? And with this setup, I'm going to define the multiplier ideal, which is going to be some ideal inside R, which is going to tell me something about the singularities of Z, or the singularities of A. Okay? And so the multiplier ideal, well, write this first. The multiplier ideal A to the T, or sometimes it's also written multiplier ideal of X, T times Z. This measures singularities of A, and it's smaller for singular A, for more singular Z. So what do I mean by that? I mean if I replace A by something that's something like maybe A defines like a some curve, like a node or something, or some kind of triple node. Sort of the more singular, the more maybe a quadruple node is more singular than a triple node. The more singular that Z is, the smaller or deeper this ideal will be. Okay. And so let me give you the actual definition. Oh, and this is with respect to this parameter T. This is a formal parameter in case you haven't seen this before. It doesn't mean anything right now. You know, it's just some way of scaling the singularities in some reasonable way. And so here's the definition. We're going to let pi from y to x be a log resolution of the pair xz, which just means that the exceptional set of pi, union with the inverse image of z is simple normal crossings. So locally, analytically, looks like coordinate hyperplanes.
The monomial with respect to the...
I actually, it doesn't matter for this definition. It's independent of... Yeah, I mean, if you want it to be locally monomial, sure. But I don't think it matters for this. I think it should be independent. But okay, yes. Make it actual simple normal crossings. And then what we define is this multiplier ideal x a to the t is pi lower star oy. Just going to stick the relative canonical divisor there. And I'm going to subtract off t times g, where, let's say, a times oy is oy minus g. I'm just going to extend the ideal up to y. And then, of course, this is, I put this coefficient here, so it doesn't really make sense to take O of a fractional, so some divisor with rational coefficients. So I'm just going to round all the coefficients up. Okay. And so this is the proper definition of the multiplier ideal, or one proper definition of the multiplier ideal. And it's sort of, 10, 15 years ago, there were sort of a lot of theorems that came out, using this to deduce consequences in commutative algebra in particular, and sort of local algebraic geometry. But it also had lots of other applications to things like the minimal model program and other things like that, the last decade or a little more as well. So, all right, so why is this useful? Well, the reason this is primarily useful is basically, this is also true in that all the higher cohomologies vanish. And so that's just sort of relative Kawamoto-Effect vanishing. And so, because, this guy is big enough. And so I'll leave that here. But this is really where the power of the multiplier ideal came from, this higher direct images vanishing. Okay. So I'm going to now give you a commutative algebraist definition of the multiplier ideal. So this is a dual definition. So now let's assume R is local. So for example, localize this ring at the maximal ideal. Okay. And so then, so this is just local duality, which is kind of like Grothendieck duality, but with local cohomology. It turns out that the multiplier ideal is equal to the annihilator, all right, of the kernel of the map from the D equals top local cohomology of R. And this top local cohomology of R, let me write this first, then I'll say a couple of words to H, maybe, I'll write it first, then I'll say some words. R gamma M. Pi lower star, OY, round down of T, G. Big N parenthesis. Okay. So let's think for a second. I have this ring R. Maybe I localize my other ring at the origin. And this ring R, maybe bad notation that I should have thought of earlier, R maps to R pi lower star, different R here, right? This is a derived R. This maps to R pi lower star OY. Okay. And A times OY is OY minus G. That's, G is effective, and minus G is anti-effective. So this guy maps to R pi lower star OY, well, round down TG. And so this map right here, this local cohomology to local cohomology, I'm just whacking it with the local cohomology with supports functor, i.e. cohomology, it has, or maybe I should look across the room here. How many people have seen sort of local cohomology before? Anyone looking completely lost? Okay, so this is just cohomology with support. Oh, you're looking completely lost, Dan. So this is just this is just like cohomology with supports functor. And the point is, there's this theory called matless duality or local duality, which tells me that this guy is sort of dual to the canonical module. This guy really is dual to the canonical module. And because my ring is, regular, dual to the canonical module, I mean, the canonical module is identified with R, and this thing is just the relative canonical module, and so on. And so the point is, if I take this map and I hom it into the dualizing complex for R, I basically get this guy with the R pi lower star in front of it, flipping signs around. And so matless duality or local duality just says, okay, I can also get the same thing by using local cohomology instead. And looking at that kernel and taking the annihilator, say. And so this is how commutative algebraists, if you ever want to communicate what the multiplier ideal is to a commutative algebraist, just tell them it's this, and they'll be much happier. Okay. I still need resolution of singularities. That's true. That's true. Yeah, they won't be that happy with you, but they might not be so scared of the relative canonical divisor. Okay. So this is a different definition of the multiplier ideal, and I'd like to say, just like to rephrase this in a slightly different way. J the multiplier ideal of a to the t, you can also think of the annihilator in R. Of the eta in local cohomology, such that a to the t times eta, this is an imprecise definition. A to the t times eta equals 0, and now I'm going to declare it's 0 in exactly this guy right here. So maybe I'll try to write this more compactly. HD pi inverse m OY round down TG. This is just that guy. I'm just writing hypercohomology and composing derived functors. So this is sort of the classes here that are roughly killed by a to the t, where you have to interpret what a to the t times a class means, which maybe it's reasonable to think it means, well, that's sort of going from here to here. Okay. So this is a definition of a multiplier ideal, and this is probably a definition most of you have not seen using local cohomology. Let me give you a definition of the test ideal that looks pretty similar. Okay. So test ideals, these are a commutative algebra invention that were later discovered to be related to multiplier ideals via reduction mod p, and I'll say precisely what I mean in a second. But let's say Rm is a local, domain or regular ring of characteristic p. And so then the test ideal, A is an ideal in R, T is bigger than or equal to 0. Definition, the test ideal, tau R, A to the T. Let me write it in a funny way first, which looks like this way, actually. And then I'll tell you maybe another way to think about it. This is equal to, and actually this is probably quite close to some of the original ways test ideals were expressed. It's the eta in top local, or it's the annihilator of the eta in top local cohomology, such that c to the 1 over p to the e times a to the t p to the e to the 1 over p to the e times eta equals 0 in HDM are perfectified. Okay. All right. For some interesting C, or some / any interesting C. Particular if C is an A, that's interesting. Basically. Yeah, C is an element of the ring. It's typically going to be an element of A. Actually, in characteristic P, with this choice of rounding, you don't need the C. But with different choices of rounding, it's absolutely crucial. So I'm just putting it there. This is called a test element. This C right here is called a test element. And it's some way of perturbing things slightly. Oh, and this should be for all E. Okay, so let me explain what I mean here. So C is just some element, which we'll come back to in a little bit. It's just some, some random element floating around. A, I'm just going to raise it to this power right here, which is which you might even think is extending it to the eth Frobenius of R. And then I'm going to take 1 over p to the eth roots of all those elements. 1 over p to the eth roots of all those elements live inside the perfection, so that makes sense. Right? So I have a map in HDM. I have a map from R to the perfection. Yeah.
What's the perfection?
Oh, I should say what the perfection. Oh, yeah, you're right. I should say what the perfection is. R perf in this case is the union of the p to the eth roots. Let's say it's a domain of all the elements in R. Okay, so it's just like perfectifying a field. We're just doing it to our favorite domain instead right now. Okay, so what I'm going to do is I'm going to take the eta in R, which are, ignoring the C for a second, which are killed by take elements in this ideal, raise them to TP to the E roughly, yeah?
Oh, okay, so the TF is only there.
Only here, as sort of the exponent of A. So this is actually very similar, I think, almost to this definition right here. Except the only difference is I'm sort of replacing my resolution with the perfection. I'm taking my A, I'm extending it to this bigger ring, and by extending it, I'm telling you exactly how I want to extend it. I want to raise powers, and I want to take p to the eth powers, or p to the eth roots. I want to raise it I want to take p to the eth powers up to scaling by t, and I want to take p to the eth roots of those elements. I mean, you can also union this whole thing together, and maybe it would be reasonable to call this guy a to the t as an element of something inside R perf. I don't know. But that's what this is. It's some way of interpreting a to the t inside the perfection. Just like over here, we had a way to interpret a to the t inside the resolution. Okay? All right. And, yeah.
Why do you need characteristic p for that? I mean, could you use, instead of using p to the e, just use any integer?
Yeah, you sort of can. I mean, so actually, yes. So this is a good point, which maybe I'll come back to later. Yeah, I mean, you could also take the absolute integral closure of R inside the algebraic closure of its field of fractions, and you could just make perfect sense of it there as well. And in the case of a Gorenstein domain, we know the answers are the same, or Q Gorenstein, or weakenings of those things. We know those answers are the same. Without that kind of assumption, we actually don't know the answers are the same. But yeah, under Q Gorenstein-like assumptions, absolutely, you can replace this with lots of other things, and you get the same answer. Otherwise, but yeah. If this somehow is the smallest possible ideal because I stick this interesting C there. It gives me a little bit of wiggle room. Okay. So let me just state a theorem here. And this is due to Smith, Hara, and then really Hara and Yoshida, and Takagi. Shunsuke Takagi. And it basically says that let me write this informally, and then I'll say some more formal words if you'd like. R, let's say you're over C to the T. If I take this mod P reduction, by which I really mean, well, for simplicity, let's say everything inside is defined over Q or Z or something. Then I can sort of spread this out to something finite type over Z, and I can take it mod P. This is equal to the test ideal of R mod P, by which I mean spread it out over Z, then take it mod P. A mod P to the T for all P big. And if you're finite type over Z, by all P big, I really mean all P big, for all but finally many P. Otherwise, you could take for an open, dense set of whatever coefficient ring you're working with, wherever you spread it out. But the point is, the multiplier ideal restricts to the test ideal doing mod P reduction for P big. For some small P's, it's not so surprising that everything's going to go wrong, because if your A, maybe your A is like the principal ideal, y squared minus x cubed, of course you're going to expect this goes horribly wrong in some characteristics like 2 and 3. Because this singularity is somehow noticeably worse there. But for P big, it's fine in some precise sense. The P actually depends on T, which is rather, makes life hard sometimes. But yeah, so this is, okay. So the multiplier ideal, the test ideal, even though they look a little different, if you think about them this way, they're actually kind of closely related. And they sort of agree in mod P reduction. So I'm going to list a whole bunch of properties of multiplier ideals and test ideals now that we might want. And I'll maybe tell you an application of these properties, at least the ones that I'm going to list. And what we're going to do, what we're shooting for is a mixed characteristic definition that's going to have all these properties and sort of, well, maybe help us interpolate between these two guys in some other way. And that's where the perfectoids are going to show up. Perfectoid algebras. Only very briefly will I mention perfectoid spaces. I'm sorry, what? Yeah, that's right. I mean, so let's say I'm working in characteristic P and I happen to know the resolution of singularities exists, then you always have this one. Or actually, even if you don't have resolution of singularities, you can define the multiplier ideal valuatively, and then you still have it this way. That always holds. Yeah. And by the way, there's also, maybe I should also say, there's something like, we had this Grauer-Riemenschneider vanishing, or this Kalmata-Fifek vanishing. For the multiplier ideal, that's also sort of built into this definition too. You might, roughly you could talk about like lower local cohomologies, and these are sort of 0 because of the C here, which sort of kills things off. Anyways, I can say more about that at the end if people remind me to. So, let's talk about properties of multiplier ideals and test ideals. Okay, so if, let's say, A is smaller than or equal to B, we've already sort of addressed this case, but let me say it explicitly, then the multiplier ideal or the test ideal of R, A to the T, whichever one you pick, is contained inside the multiplier ideal or the test ideal of R, B to the T. Okay, and this is a trivial consequence of any of the definitions. And if T prime is bigger than T, then the multiplier ideal or test ideal of R, A to the T prime, say, that's going to somehow make the singularities worse, just like raising an ideal to a power you'd think would make the singularities worse, is going to be contained in the multiplier ideal test ideal of R, A to the T. Okay, so these are some really basic properties, which are essentially trivial from the definition. Here's also one that's pretty easy to see from the definition. A is actually contained inside the multiplier ideal test ideal of R A to the 1. Yeah. I mean, from the multiplier ideal definition, which fortunately is still up here, and of course I'm using here that R is regular. From the multiplier ideal perspective, this is very easy. Because if I didn't have this relative canonical guy here, I took a log resolution and I extended it out and pushed it forward, I just end up with the integral closure of A, which is bigger than A because it's the integral closure. If I put a relative canonical guy here, that relative canonical guy over a regular ring is always effective. So it's always going to make it even bigger still. And so that's why you get this first containment here. And something, I don't know, I mean, it's kind of, you have to do two dualities to do it for the test ideal. Because you have to do, you sort of flip things and you take an annihilator, but it's also essentially equally easy here, up to a little bit of tweaking. What do you mean? From the test ideal? Well, no, so test ideals are not always integrally closed. No, paper of Mustatsa, well, yeah. In this context, Mustatsa and Yoshida showed that in a regular ring, every ideal is actually the test ideal of some A to the T. So it's, yeah. Whereas, Rob had a student who told you, he gave some actually syzygetic conditions on when certain ideals could be multiplier ideals. So it's a bit different that way. Okay. One more property. Let's say if A, if A is prime and height of A is H, say, then the multiplier ideal, or the test ideal of R, let me write this down in just a second. A, this is called the symbolic power. It appears in my title, so I'll explain what it is in just a second. This guy right here is actually contained inside A. And I just erased my definition of the multiplier ideal, which is slightly unfortunate. But, okay, so let me write over here what the symbolic power is, just so I keep it. A to the round brackets, which read symbolic power m, these are the functions in R which vanish generically to order m at V of A. Okay. So these are the functions which vanish to order m basically at all points of A. And so if you think about it for a second, at least from the multiplier ideal perspective, okay, if you blow up a prime ideal, and then you do a further log resolution if necessary, there's going to be one unique divisor dominating that prime ideal. Okay? Yeah. And so if you take that sort of special divisor dominating it, and you have a function which vanishes to order m at that along the points there, it'll vanish to order, the pullback of the function will vanish to order m along that divisor. On the other hand, the relative canonical for that divisor is h minus 1, codimension h minus 1 here. And basically, you're doing h minus 1 minus h, that gives you a -1 coefficient, which means when you push this down for the multiplier ideal, you're going to end up with functions that vanish at least to order 1 at that point. There might be some other conditions, too, coming from other exceptional divisors, but that one's going to be free. And so you get this containment right here. And finally, we need one more that I'm going to write today, sub-additivity. And this is all right. I'll have to say a little bit about what I even mean by this. This is contained inside a multiplier ideal or test ideal of a to the s times the multiplier ideal or test ideal b to the t. It's contained inside that product. And let me write this in a particular special case. The multiplier ideal or test ideal of a to the t times an integer n, this guy is contained in the multiplier ideal or the test ideal of a to the t to the n. Just the nth power of this ideal. Okay. Now I'll say maybe a thing or two about the proof of this a little later. But these are a whole bunch of properties. Most of them are very basic properties. This one is a bit more work. This is actually a theorem. These are all pretty much easy observations. I should say what this actually means here. I have two ideals and not just one. There's a couple ways to interpret this, and all of them are correct. You could just pull back a or b to your simultaneous log resolution of both, and subtract off, s times the divisor of g, and t times the divisor corresponding to b, and that would be fine. Another way to do it is, okay, let's say these are rational numbers, which is also a reasonable assumption, and then you could just, find a common denominator, and yeah, that'll also work fine too. And, I don't know. Put m's and 1 over m like this too. If they're rational numbers, that's fine as well. Okay, so, and from this you easily deduce this. And so, what do I want to do then? Well, one of the applications, I guess in around 2001, of Ein and Lazarsfeld and Karen Smith was the following. And so it's basically a formal consequence of these properties, which if I have time at the end, I'd be happy to show you, of Ein, Lazarsfeld, and Smith. And what it said is R is a regular ring, ring in characteristic 0. Well, and Q inside R is prime of height h. Then, for all m bigger than 0, Q to the symbolic mh is contained inside Q to the m. And so Ein, Lazarsfeld-Smith proved this. I think it was inspired by some earlier work of Arana Swanson, which basically said for every ideal in any ring, there is some bound, some number that works to give you this kind of containment property asymptotically. But it depended on the ideal. And Ein, Lazarsfeld, and Smith, as a really unexpected, I think, application of multiplier ideals, maybe Rob can say how expected it was, they deduced that you could actually just use this h right here, the height, as a uniform bound. And in particular, you could use the dimension of the ring as a uniform bound for all ideals. And so I think, very shortly after Ein, Lazarsfeld-Smith's result, Hochster and Huneke, two commutative algebraists, proved the same thing for over a field. For any regular ring containing a field, they were able to deduce the same thing. They, deduced even a little bit more, maybe. So Ein, Lazarsfeld-Smith did things of finite type over fields, and Hochster-Huneke did things in characteristic P, and then by some approximation, we were able to get all rings containing a field. Okay. But the mixed characteristic picture was left open. Oh, and by the way, there are actually like geometric consequences to statements like this, because you could think of maybe your ring as being like a polynomial ring, which maybe think of as, and then if I take Q to symbolic, this says, certain functions which vanish along some subvariety of projective space, so some hypersurfaces which vanish along, some hyperspace of some degrees actually have certain bounded dimension, or vanishes to some order along some subvariety, they actually have sort of bounded degrees, is sort of almost what this could be interpreted as saying. Okay. So, we'd like to do this in characteristic P. Let's say all of it. We'll do all of it in characteristic P. And I've still got 20 some minutes. Okay. So, why is now the right time to do anything in, or not characteristic P? We want to do this in mixed characteristic. So now is sort of the right time to try to look at some of these questions, because there was this very recent theorem of Andre and then Bhatt sort of improved the theorem, improved the generalization, and I'm going to state both of them. This was just last summer or early fall. If R is regular, R is a subset of S, and let's say this is a finite inclusion, which means S is a finitely generated R module. Then this splits. So this was called the Direct Sum and Conjecture. It was conjectured, I don't know, more than 30 years ago by Mel Hochster. And this conjecture actually really inspired a lot of research in commutative algebra over the last, many decades. And so it says, if R is regular and S is any finite extension, there's a splitting. This is of course almost trivial to prove in characteristic 0 because you have the trace map. And, you have the trace map which sends it back there, and it's going to send 1 to the degree, and you invert the degree, and you're fine. In characteristic P, it's not obvious, but it's not that hard. You take Fabinii and you do tricks that actually look very similar to this. It's sort of maybe even the origins of test ideals and tight closure theory sort of came out of Mel's study of this kind of question, Mel Hochster's study of this kind of question. And so this is what Andre proved over the summer. And then Bhatt simplified Andre's proof quite a bit, and he also gave the following generalization. If R is regular, pi, and now, we're in any, this is just any ring, pi from y to x, or y to r, or to spec r, is proper. And now I'm going to have the same problem with r's and derived homs, but r to r pi lower star oy splits in the derived category. So what do I mean by splits? I mean sort of the same thing I mean here. Maybe splitting doesn't quite make sense in the derived category. I mean there's a map in the derived category like this, so that this followed by this is the identity. Okay. By the way, in characteristic 0, this condition right here, this splitting condition, is equivalent to rational singularities. So it's the theorem of Chandra-Kovács and Bhatt as well, which proves this is... So this kind of splitting condition, you could view these theorems as basically an assertion that regular rings and mixed characteristic have rational singularities. Which, if anything has rational singularities, you would think regular rings have rational singularities. So maybe it's a reasonable thing to hope for. Okay, so I need to, and what do? They use perfectoid algebras, perfectoid spaces, and the machinery therein, Schulze's recent, some of Schulze's recent work and breakthroughs, and they use that to deduce this. So, let me tell you what they proved. Maybe I'll go, I guess I want to keep this definition up, just for comparison. Okay. So one of the things that comes out of their proof, or at least with a teeny bit of additional work, maybe taking a direct limit, is if A is regular, say complete, of mixed characteristic, and if you are uncomfortable with what I'm saying here, i.e., you could take R to just be, maybe the p-adics, formal power series, and maybe d minus 1 variables. I put a d minus 1, so this ring has total dimension d, because p is sort of like an extra variable in this ring. So if I have a regular complete local ring of mixed characteristic, then there exists some extension, A infinity, over A, which has a bunch of nice properties. So make it even, a bunch of nice properties. Okay. And this guy is something called integral perfectoid. Okay, so this is a perfectoid A algebra. And I'm going to tell you some of the properties it has as well, which is sort of the key point. What does perfectoid mean? Maybe I don't want to write down the definition, but the main point is, if you go mod P, if you take this ring mod P, remember P lives in A, so it lives here. If I go mod P, there's going to be a Frobenius, because I suddenly have a characteristic P ring. And it means the Frobenius is surjective mod P, and the kernel of Frobenius is understandable. In some precise, I could write that. I could tell you what it is. In fact, maybe depending on how generally I want to write this. So it just tells you that mod P, this guy is perfect, and there's some other properties too. But that's perfectoid integral is some kind of integrality condition, or at least in some cases can be interpreted as an integrality condition when I invert P. So sort of integrally closed when I invert P. It's roughly the idea. So this is some kind of integral perfectoid such that, okay, and this is the important part, all, or maybe a chosen collection of elements of A have systems or have compatible systems of p to the eth roots. Which means any element here, I can take its p to the eth root, and there is a p to the eth root of that element living in this ring. And that element also has a p to the eth root, and so on. I can take an infinite system for any element of A, say. But, okay? So, okay. This is extra data. This is not part of the, so for a perfectoid, you need at least some elements to have p to the eth roots. I'm actually requiring all elements have p to the eth roots, or at least a specified collection of interesting elements have p to the eth roots, is really what I need. So this is not part of the perfectoid definition, definitely.
The question is,
oh, sorry.
The choice of the p to the eth root
Is part of the structure that you put in it, or no?
No, unfortunately, yeah, at some point I might say something about that, but yeah, okay, I should say this A infinity is not going to be a domain too, so this is actually kind of annoying. There might be sort of different directions of taking p to the eth roots, and so it's actually, it can be kind of a hassle sometimes to work with this thing. Okay, so this is a perfectoid algebra. And two, let's see, I believe, it should be a local perfectoid. Integral perfectoid I should also say it's periodically complete. That's also built into the perfectoid definition. Well, I don't know. Maybe it's not. Well, okay, let's see. A infinity is almost faithfully flat over A. So we all know what flat means. Built into this perfectoid machinery, sort of underlying it, is this theory of almost mathematics, which creates many opportunities for puns during talks, because then you can almost prove something and then you actually proved it. So let me just say, what do I mean by almost faithfully flat? Okay, so there's some kind of uniformizer which... Okay, so you have some kind of pi, which is like p if you're dealing with a ramified local... I don't know. Okay, fine. I'm just going to ignore the ramified case. So I fix a collection of p to the eth roots of p. Okay? And I actually sort of fixed it in my original construction. And what you want is that for any module, the p to the eth roots of p actually kill the tors. So, you think of taking higher and higher roots, this is getting closer and closer to 1. It's harder and harder to kill things when you take more and more roots. This guy is 0. That's what I mean by a module being almost 0, at least in the unramified case. Otherwise, I have to be a little bit more careful. But I'm going to try to skip some of this gory detail that I wrote in my notes. Okay. So, and there's another property too, which is... No, yeah. Well, that's correct. The faithfully is not. Yeah, I don't know. Yeah, well, no, I mean, let's see. It is, yeah, it's still faithful. I mean, this is a.
Depends on something which is almost 0, then that thing should be almost 0.
Yeah.
So you need almost a fifth.
Yeah. So it's almost faithful and almost. Yeah. Okay. Okay. So this guy is equal to 0. That's what almost flat means, for instance. And there's another condition too, which is just basically that A infinity is sort of almost a Cohen-Macaulay A module, which you could think of as, I don't know, at least in this case, you could say p to the t x1 through xd minus 1 is an almost regular sequence. Oh, was this faultings? This is faultings. And Gabber and Romero have a very large book about it on the archive. Okay. So, what I want to do is I want to replace our perf by this A infinity in this definition right here. And if you make this choice, then you can define a mixed characteristic test ideal. So let me actually write this down precisely. Okay, so my tau perfectoid, test ideal perfectoid, or multiplier ideal perfectoid of A is my mixed characteristic ring, A to the T, same setup, is going to be the annihilator. This is a definition. Thanks. It's the annihilator of eta in here, such that 1 over p to the 1 over infinity, or if you want, you could take var pi if you're dealing in the ramified case where this is an appropriate guy, times a to the t, and I'm going to have to tell you how do I interpret a to the t, times eta equals 0, and this is going to take place in HDM A infinity. Yes, R is A. So it's the same definition as I gave for the test ideal, the same definition I gave for the multiplier ideal, where the problem is I had to do what I told you in both those cases. I have to tell you how do I interpret a to the t in this ring. And we have a couple different choices. So how do we interpret a to the t? And one of them turns out to be easier to work with for proving some of these properties. And we believe we can now show that they're equal, but that we haven't written all the details down on that yet. We only realized last week that we could actually show that these two things are equal. But let me write them down. A to the t, you could say, is a set of all f in A infinity such that, f is, yeah. Okay. Let me see how I wrote it in here. So let me write it this way. It's pi, or p to the 1 over p infinity times f times eta equals 0. So I'm just going to explain what this is, where f to the 1 over p to the e, where f is in a to the t p to the e, and this guy is part of a compatible system of roots. Okay, a to the t is the set of all f to the 1 over p to the e's, where f is in this guy, and f is part of a compatible system of roots, so I could take further roots if necessary. Okay. So it's a set of p to the eth roots of elements of this. So it's exactly the same thing, roughly speaking, that we did for the test ideal. And so there's another option too, which is easier to work with, and like I said, I believe we can now prove they're the same, but it's enough for applications anyways. Oh, and I left out an important point. Shoot. A to the t plus epsilon, p to the e. So you can choose this for different epsilons, and as you shrink epsilon, Noetherianness guarantees that it stabilizes. Okay. I'm giving you a precise definition. So here's the other definition, which is much easier to work with frequently. So we're going to fix F1 through Fn generators for A. And then I could also interpret, fix once and for all compatible systems of roots, of p to the e's roots, of each one of these elements, and then we interpret a to the t to be f to the 1 over p to the e, where f is just a product of fi, I equals, there can be repeats here, I to round up of t p to the e. So basically monomials of the right degree in order to give us this thing. Okay. So we're only going to multiply by monomials, and of course it's not, why this is sort of troublesome and not so nice to work with, is this sort of obviously depends on the choice of generators, at least a priori, and the choice of p to the eth roots of those generators we picked. And we now believe we can show it actually is equal to this one, and so it's independent of these choices, but it makes things easier. Okay, so what's the upshot? All these hold for a perfectoid test ideal, or perfectoid, or tau perfectoid R a to the t. So all these properties we talked about holding for multiplier ideals and test ideals also hold for this perfectoid guy. Some of them are obvious. this is just as obvious as these first two are, well, this one's just as obvious as it was in all the other settings. This one is about as obvious as it is in characteristic P. Not quite as obvious as, or I'm sorry, yeah, oh yeah. These are obvious. This one's as obvious roughly as it is in characteristic P. This one is a lot of work, and I'm going to take the last couple minutes to say something about the proof. And this one is about as hard as it is in characteristic P. So I should say something about subadditivity. How do we normally prove subadditivity for multiplier ideals? Well, we take the product of x cross x, and we sort of do a to the t on one of the x's and b to the s on one of the x's, and we restrict to the diagonal. And you can prove the same thing for the test ideal roughly by the same way. That doesn't, at least Linquan and I didn't see how to do this for test for the perfectoid guys, because we could take our R and we could tensor it over ZP maybe, or maybe some ring of vectors or something, with our ring itself, and just sort of we could play a game there. But the problem is P can sort of cross the tensor product. And when P crosses the tensor product, if P shows up in these ideals, it kind of screws us up. And so we didn't quite get the same thing. Fortunately, in characteristic P, there was a different proof of subadditivity due to Shinsky-Takagi, which didn't rely on restriction to the diagonal. And we were able to actually, in some ways, even simplify that proof. And it's actually almost easier in mixed characteristic. Our proof is even easier than the characteristic P one. But this one is actually quite involved. This is actually the most involved. Shockingly, this is the hardest part. It's easy in characteristic P. It's essentially trivial in characteristic 0. And in mixed characteristic, well, it was kind of hard. And the proof of this is actually related to this independence that I mentioned here. And I should say, as a consequence, we get the symbolic power bound if R is any regular ring, regular excellent, I guess. We actually use excellence. Q inside R is prime. Height H. Then we get Q symbolic MH is contained in Q to the H. And so, roughly speaking, in the same way you get it out of these things, you also, in characteristic 0 and P, you also get it here. What? Oh, I'm sorry, yes, Q to the, yeah, thank you. I need another loop on my H/N, which is indistinguishable the way I wrote it. Okay, and roughly speaking, it's a little bit more work if you're using this generator definition, but roughly speaking, the same way. You just have to choose your generators compatibly as you take higher and higher symbolic powers. You have to throw in the previous generators in the appropriate way. Okay, so let me say a teeny bit about this, this containment right here. And then I will, I'm already out of time. So maybe I shouldn't say anything about this containment right here. Now, can I have like 2 minutes to say something about it? All right. Okay, I'll say something about this containment right here. Okay, so here's the idea. We had A going to A infinity. We're multiplying by some f to the 1 over p to the e. We're going to A infinity. For now, let's assume that p is in my Q. Right? I'm trying to show something like this. Let's say this is prime. I'm going to assume that p is actually in there. Okay? This will make life easier. Otherwise, there's no way I could say run through this proof in this case, this time. Okay, so this is basically the mapping I take local cohomology of, and I'll take kernels and something like this, where f is in one of these ideals here. Okay, so what I'm going to do is I'm going to blow up, or take maybe the normalized blow up. Maybe I should put this in a bigger space. I'm going to take the normalized blow up of Q. makes perfect sense in A. So I have A, going to A infinity, going to A infinity. And I can take the normalized blowup of Q, r pi lower star, OY. And let's say E, so Y to X, maybe normalized blowup of Q. And let's say E is the divisor, is sort of the unique divisor lying over Q. And so then I can, I can twist right here by H times E. That's an effective divisor. That makes sense. I have this map right here. Okay. And this is times F to the 1 over P to the E. F is any sort of element inside Q to the symbolic HM to the 1 over M. I mean, it's one of these elements which sort of vanish to the right order there. And the point is, well, I could also blow up A infinity at the same ideal, and maybe I'll call that r pi lower star OY prime, and I'll maybe even put it here. So I have A to A infinity multiplication by this F. I go to r pi lower star infinity OY prime. And I'd like to sort of conclude that multiplying by F, which is sort of like, allowing sort of poles of order 1 over F, I'd like to sort of include, I get a map here. It's actually not quite obvious. At first we thought it was obvious, but then I realized it wasn't quite obvious. And the point is, this is a horribly non-Noetherian ring with p to the eth roots of sort of everything in sight. So this blowup is sort of very far from being normal. And so you have to do a little bit of work. If you do a slight further blowup, if you blow up some element, if you throw a couple more elements in A infinity that are integral over your ideal, you can make the blowup just a little bit bigger, and you can get a map. Maybe I'll call this guy infinity like this. But just blowing up a teeny bit more if it didn't happen to include. And because the point is, F has, F vanishes to order, roughly speaking, at least HE along, at least H along E. So you expect a factorization like so. And then you just slap on HDMR, or like this guy, and you'd like to conclude basically that this map from here to here, you'd like to conclude that this kernel from here to here, after you slap this guy on, is roughly the same as that kernel. But they're almost the same, because this guy is always dominated by R gamma sort of SPA A infinity, and I can't, so perfectoid spaces showed up very briefly. There's some kind of perfectoid, O of SPA here, comma O. So Schulze has the statement that the pre-sheaf on the SPA is a sheaf, which in particular sort of tells you that the higher direct images are sort of almost zero, which means they're killed by infinitely small powers, and we built in this 1 over p to the infinity into this. And so this is an almost isomorphism. And when you apply HDM, it's still essentially an almost isomorphism. And because we built it into our definition the right thing, this kernel right here is the same as this kernel right here. And so once you have this containment, you just dualize and you get the same containment you got from multiplier ideals. And so, all right, I'm sorry I went 5 minutes over. Thank you very much for your attention.
Any further questions?
What's the logical relationship between the results of Andre and Bhatt and this? That's ideal.
So there is a. I'd have to get in. Okay, I'd have to.
Besides just the fact that they said.
Okay, no, there actually is a specific logical relationship. This A infinity really plays a role very similar to R infinity. The perfection of R and the characteristic P proof. in their proof. It looks, it plays a very similar role somehow. And I should also say, this trick of factoring through the SPA, that's also a key step in Bargov's almost, the derived direct sum and split into two. So why is this the right thing to do? This is the right thing to do also because, okay, what's good about like resolution of singularities or R infinity? You have this sort of vanishing machinery built into it. And in characteristic P, I think I erased it, but you have this almost faithfully flatness, which actually implies some very Grout-Riemanstein vanishings as well. And so if you sort of take that all together, you say, oh, this looks kind of like something that we could formally run the kind of arguments we ran multiplier ideals and test ideals for before, because there's this vanishing built in. And so that's, so we certainly are using the analog of that to prove subadditivity, for example. And a bunch, and actually even some of the other things which I erased on this board. Some of the other ones also absolutely use this vanishing, at various stages to get these trivial containments. You have to use this vanishing.
Maybe just a quick question.
Yeah.
You stated Bhatt's result on splitting of.
Yes.
So, how is this related to the mixed characteristic case?
Oh, the mixed characteristic case was the only case left unproven before Bhatt's result, or Andre's and Bhatt's result. So the direct sum and conjecture is easy in characteristic 0. Its work in characteristic P, which later helped inspire tight closure and all sorts of other test ideals in general, sort of came out of that out of Mill's work at some level.
There's no implication one way or the other for.
Well, no. I mean, you could also. It's just, certainly you can talk about perfectoid things in characteristic P. So I'm sure almost certainly Andre and Bhatt result also work in characteristic P directly, but it's a ridiculous way to prove things. I guess you could also ask questions like, is this ideal we wrote contained in the multiplier ideal? Let's say you had resolution of singularities, or you could find a value into. And the answer is basically yes. And it's because blow-up factorizations, tricks like this.
All right, well, I suggest that further questions will be addressed over time.